right? So you can see over here is going in this direction, moment in the Y, and this is compression, this is tensile. So you know that element A, right, stress X of element A due to the moment will be under what? Compression. Okay. You analyze all this now. Later on, when you calculate your stresses, it will be hopefully, not hopefully, I'm very sure it'll be definitely easier. Okay, so now anything else? That's it. There's nothing else we could do. Then we are going to look at another view now. Okay, we're going to look at a different view now. So I'm going to copy this over here. So the next view that we are going to do is we're going to view this in the so let me sort out our transformation first. X, Y. So we are going to view in the YZ plane. Okay. So view. So now I'm going to draw it again. Okay. So this is our Y. And there is our Z. Okay. And then you got two lines over here. And over here, this is your element A. And then this is your neutral axis. All right. So there's your neutral axis. And then you put in all your forces again. Okay, you put in all your forces again. So we have a 100 kilonewton over here. And then you have a 25 kilonewton. And then you have 8 times 10 to the power 3 Newton. Okay. Then you have to be careful, okay, down here. So down here you have to be really careful. Okay. We know that, so if we look at here, this is our rotation in our X, right? So we know that we are going to have a moment, right, due to the 100 kilonewton and the 25 kilonewton, right? So the 100 kilonewton, the perpendicular distance is this distance over here. It's towards the what? Towards the centroid, right? You have to be careful, not towards the element, okay? Because the perpendicular distance is perpendicular to the what? Centroid, right? So this distance over here, I think I'm going to look at our, so that distance over there is 0.166. Wait, not 0.166. It's 0.205 divided by 2. Okay, so this is 0.205 divided by 2, right? Now, this moment, the 25 is going to be towards the what? Towards the element. Why? Because the perpendicular distance is what? Parallel to the neutral axis, right? So this distance is equal to, we know that this is equal to what? This is equal to 0.5 meters. So you have to be really careful. A lot of students make this mistake. Okay, a lot of students will bring this up to the what? Up to the element. Okay, a lot of students. Okay, I've been teaching this for quite a while now. A lot of other students. I'm not saying that you guys, but I don't want you all to make the same mistake. Okay, it's a very common mistake. A lot of students, they will say, "Oh, Eugene, if that's the case, this is the perpendicular distance." No, it intersect the what? The neutral axis. Whereas the 25 did not the perpendicular distance did not intersect the what? Neutral axis. That's why you use towards the element. Okay. So I'm going to declare that going clockwise is positive. So I mentioned about moment in the x direction is equal. So all these are relative to the what? To the element. Okay. So force 100 times 10 to the power 3. Distance is 0.205 divided by 2 plus by 0.5. Plus by 25 times 10 to the power 3 multiplied by 0.5. Okay, so this will be equal to 100 power 3 times 1.205 divided by 2 plus the 25 power 3 times 1.5 is equal to 2275, 22.75 times 10 to the power 3 Newton meter, and in this direction. So if it's that direction, so you immediately draw this, right? So this is moment in the x direction. This is compression. This is in tensile, right? So you know that it's in tensile. Okay, so you know that this is going to be stress Z of element A, right? Is going to be in what? Tensile. Okay. A lot of students make mistakes of this is the center, the distance, the perpendicular distance. Okay. So next you look at Vy. All right. So positive is going down here. Summation forces in the y direction. So this is equal to This is equal to 25 times 10 to the power 3 Vy. All right. So this is also equal to your Vy. So now, is it going to be equal to 0? Now you have to be really, really careful down here. Okay. So I'm going to copy the cross section. Now these are thin wall analysis. You have to be very, very careful. So this is our Vy, right? So looking at here, this is your Vy. And if we draw the Q will flow this way, yes or no? Right. So your element A, right? Your element A will be over here, right? So we know that the shear, right, which is equal to Vy over Ixx Qx divided by T is not equal to 0 for element A. Right? It will not be equal to what? 0. Okay. So once you have everything already, there's nothing else for you to do already. Okay. There's nothing else. So now you have all your forces. Okay. You have all your vectors. You know what is a moment, what is shear force, which one is inducing shear force, which is inducing a moment, and which is inducing axial load. Now is to assemble everything together. Okay. So I'm going to look at the cross section. So I'm going to copy this cross section. Hey. Probably I could paste down here. Okay. All right. So we are going to find out what is our stress in the Z direction, which is equal to PZ over A, right? Plus minus MX over IXX multiplied by Y plus or minus MY, sorry, over IYY multiplied by Z. That's why you have to like remember the formula. I taught you guys how to remember. So we have our px, right? We calculate, we analyze our stresses. We realize that we have our px. So if we look here, right, we have our px, which is equal to 100 times 10 to the power 3. Okay, so minus 100 times 10 to the power 3 divided by the cross-sectional area, which we already found out to be equal to what? 5320 times 10 to the power minus 6. 5320 times 10 to the power minus 6. Okay, so this is where our element A is. Okay, so this is our element A, right? So let's look at moment in the x direction. Okay, so where did we calculate our moment? So if we look at our moment in x direction, it is 22.75 times 10 to the power 3, and it's in tension, right? So, okay, moment in x direction. So we know this is plus. It is 22.75 times 10 to the power 3, right? And the y distance, it is this distance from here to here, right? This is our y distance. So it's d divided by 2. So we find out what is our d is 0.205 divided by 2. So this is equal to 0.205 divided by 2. A lot of students make mistake in terms of the y, okay? Like in your term test also, I realized that. Then your IXX, so you assemble your IX, 40.8 times 10 to the power minus 6. Okay. Then MY, we're going to look at MY. So we did analyze the MY, right? So MY will be under compression, right? MY will be under compression. Sorry, this is stress Z. I do apologize, right? So MY will be inducing a compression. So that's where you put a minus sign down here, right? So the MY is equal to 9600. Okay, 9600 divided by IYY. Okay, so we are going to go back, look at our IYY, 9.03 times 10 to the power minus 6. Then it's in the, this is in the x distance. So it is, so now we have to find the distance between here to here. So BF is 166, right? So 166 is our BF. The distance from here to here is equal to 75 millimeters. Okay, so the y bar, the x distance is equal to 0.166 divided by 2 minus by 0.075. Okay, now you see how critical to analyze, right? We can write up the formula easily knowing tension or compression, because we analyze the structure already. We look at here, okay, we say that, okay, this is under tension, is plus or minus, right? We know all this already, okay? So that's how I will strongly advise you all to do your calculation, okay? This is my strong advice. Okay, so this is equal to minus 100 power 3 divided by 5320 power minus 6 is equal to minus 100 power 3 divided by 5320 power minus 6 is equal to 18.797. Okay, then plus by 22.75 power 3 times 0.205 divided by 2 divided by 40.8 power minus 6, 57.154 times 10 to the power 6. And then minus 9600 times by 0.166 divided by 2 minus 0.075 divided by 9.03 power minus 6 is equal to 8.505 times 10 to the power 6. So this will be equal to minus 18.796 power 6 plus 15.154 power 6 minus 8.505 power 6 is equal to 18.797 plus by minus 18.797 plus 57.154 minus 8.505 is equal to 29.852 positive times 10 to the power 6 Pascal. Okay. So what we have found now, right? What we